A huge thanks to Brian for sponsoring this video. Once again, a competitive mathematics problem. Once again from the Czech and Slovak IMO, but this time from the 1999 nationals. And this problem right here has more to it than meets the eye. More about that during the video. Now let's take a look at this problem. Let p of x be a quadratic polynomial with p of -2 being one of the roots equal to 0. Now we have to find all the roots of p of, and now we plug another function in, x squared plus 4x minus 7 is equal to 0, given that it has at least one double root. And this last part right here, at least one double root, if you don't read carefully, you're going to run into a little trap. I think this was a totally nice problem. I really enjoyed this one and I hope you do too. Try it out for yourself, and once you're done, keep watching the video for the solution. By the way, if you're not yet familiar with quadratic functions, competitive mathematics problems, etc., why not make sure to check out the contents of today's sponsor, Brilliant. More information at the end of the video, but link down there in the description to check it out. But if you're still ready, then keep watching the video. Now we are going to dive right in. So how would you start with a problem like this? Well, the easiest way is to start with the fundamentals. Now p of x is a quadratic polynomial, meaning p of x is of the form, well, a times x squared plus bx plus c. That's a generalized quadratic polynomial. And now we have another piece of information given, namely that p of -2 is equal to 0. Now what that means is, it's a root, and we can turn this into linear factors right here, the multiplication of linear factors, this p of x. Meaning p of x is also of the form a times, and now we have x, and then minus the first root, so plus 2 in this case, minus 2, times x minus the other root that we don't know anything about. And this is the part where I stumbled a tiny little bit later in the game. Okay, this right here is what our p of x looks like. That's a good foundation, and now we can go ahead and get started by plugging our x squared plus 4x minus 7 into this equation, and then we are going to see under which conditions this is actually equal to 0. We are going to call this polynomial x squared plus 4x minus 7 r, meaning if we were to plug r into our p of r, then we are going to plug the r into here. By the way, our original equation, or finding the roots, is completely independent of our factor a that we have right here. You could say, you can factor it out from the start, then you have x squared plus b over a, x plus c over a, then you can start using the quadratic formula and turn this into linear factors, just as a little piece of information. This is why I factored out the r, but but still left it here. Now if we were to plug in our r, we are going to get a times, and now we are going to get we are going to plug the r into here, I'm sorry, r plus 2, and then r minus x naught. Okay, by the way, without loss of generality, a is obviously not equal to 0. Okay, just as a matter of fact, if it were 0, then it would be a linear function, not a quadratic polynomial. And now we can go ahead and start solving this equation. This right here is equal to 0. Now, at first, why not find out what the first root is going to be? Now we have a concrete piece of information given. Multiplication of things is exactly 0 if one of the parts is equal to 0. So we are going to see when r plus 2 is equal to 0. Meaning r plus 2 is the same thing as, we know what r is. R is x squared plus 4x minus 7. So x squared plus 4x minus 7 plus 2, this is minus 5. And we want to see when is this equal to 0. Now we can make use of the quadratic formula here, giving us overall that the first two solutions are, okay, we are going to get -2 plus or minus square root of, then 4 divided by 2 is 2, squared is going to give us 4, 4 plus 5 is going to give us 9 overall. Meaning this right here is the square root of 9, which is 3, meaning two solutions to this being equal to 0 are on the one hand x1 being equal to -2 plus 3, which is 1, or x2 being equal to, okay, then we are going to get -2 minus 3 is -5. Now what does this mean for us? Well, our polynomial here is exactly 0 if either x1 is equal to 1 or x2 is equal to negative 5, meaning our P of r is going to turn into the following thing. A times, now we are going to get x minus the first root, x minus 1, and then x minus the next root, minus 5 is plus 5, and then times x minus x naught, r minus x naught. Okay, we plugged r in. We don't know anything about this part yet. Now those are most definitely, with the first condition that we have given on our quadratic polynomial, the first two roots of our polynomial, 1 and negative 5. But now we need to find the other roots. And here is where a bit of casework comes in. And this is where I stumbled a tiny little bit. I thought I was done before I was actually done. Now the first thing that came to my mind when it comes to double roots is to take a look at the derivative of the polynomial. That's a fun little fact, but it doesn't help here. I'm just going to mention it really quick. Suppose we have a polynomial, let's say f of x, which has some kind of double root, meaning our polynomial is of the form x minus x naught squared and then x, no, this is just some kind of tail. We still have this going. Okay, those could be other factors. Let's call it g of x. If we were to differentiate this now, we are going to get that f prime of x is equal to, okay, we are going to get 2 times x minus x naught times g, and then we are going to get plus x minus x naught squared times g prime. Now we can factor out x minus x naught, and what we have left is 2 times g of x plus x minus x naught times g prime of x. This is just another polynomial in some kind of way. Multiplying this by another polynomial, let's call it h of x. Meaning what it means for double roots. If we have a double root of a polynomial given, then this also means that the derivative of the polynomial is going to have the same root as one of the double roots, okay? This has to do with the algebraic multiplicity of the roots. But this fact doesn't help here, even though it's a nice fact. I think it doesn't help here. I tried it out, I couldn't get anywhere with it. But there's an even easier fact that has to do with double roots. And for this, what we are going to do is our first case, that we are going to suppose that this double root that we are going to have lies exactly in here. This right here is our double root, meaning we are going to say that 1 and negative 5 are just single roots. They don't have some kind of algebraic multiplicity coming with them. So the first case, x1 equals to 1 and x2 equals to negative 5 are single roots. What does this mean in general? Namely, r minus x naught squared is going to be the double root, you could say. Now what does it mean for something to be a double root? Well, let us write out what r minus x naught actually is in our case. We know what r is. This is x squared plus 4x. And then we are going to get minus 7 minus x naught must be equal to 0. I mean, we want to find out when is this equal to 0. Okay, this is the part of the roots that we need to use here. Now we are going to solve the quadratic formula. Meaning we are going to get x, 3 and 4 being equal to, okay, let's go through the quadratic formula once again. This is going to give us negative 2 plus or minus the square root of, and then we are going to get 4 plus 7 plus x naught. Now, when do we have double roots? Well, when the algebraic multiplicity of our root is exactly 2. Meaning the discriminant right here is going to be equal to 0. Because then both roots that we would have, both solutions, fall onto the same solution. Because the plus and minus 0 really doesn't change anything. Meaning x3 and 4, the two solutions, are both going to be equal to negative 2. Meaning we want this to be equal to 0. x naught plus 11 is equal to 0. Or in other words, we want to have x naught to be equal to negative 11. Meaning, if this right here is the case, then we are going to have double roots. And those double roots are going to lie exactly at, in our case, negative 2. Yeah, and this is when we can plug in our negative 11 into our x naught, and then we are basically done. Meaning the next two roots that we are going to get, or our double roots, are going to be at exactly negative 2. Those are going to be the double roots. Now, this is where I stopped originally, but as mentioned before, there is more to this problem, because this is not the only case when we can have double roots. There are actually other cases. Namely, we could have, it says that it has at least one double root. We could also have that x minus 1 and x plus 5 are both double roots. This is something that we can have. Meaning, on our original quadratic polynomial, we have p of negative 2 or negative 2 being a double root in general too. So case 2, x1 is equal to 1 and x2 is equal to negative 5 are double roots. And this happens exactly when x0 is equal to negative 2 is a double root of p of x. I hope you can see how this works out. Okay? We can only have this or those two being double roots, meaning we have two double roots in our case, if x0 is equal to negative 2 is a double root of p of x. This just has to do with this fact that we have here, namely that if it were a double root, then we would have that p of x is exactly a times x plus 2 squared. And if we were to now plug our r into here, we can go through the same procedure once again, meaning we are going to get that x or r plus 2 is only 0 in the case if x1 is equal to 1 or x2 is equal to negative 5. Since we have a square here, we are going to get x minus 1 squared times x plus 5 squared. Yeah, this is the other case that we could possibly have. And then this got me thinking, this is not the only case, or those are not the only cases that we could possibly have. What about the case when only x1, x1 being equal to 1 is a double root? This is our next case, case 3. x1 is equal to 1 is a double root. Okay. This is rather tricky. What does this mean in our case? If x1 equals to 1 is a double root, then we are going to have that p of r is, we already know what p of r kinda is, because we know that p of negative 2 is equal to 0 on the original polynomial, meaning p of r is a times x minus 1 times x plus 5. But now we have an algebraic multiplicity of our root x1 of 2, meaning p of r is most definitely a times x plus 5, this is one of the roots by our first condition, then x minus 1 squared, and now we still have one left that we don't know anything about. We are going to call it x minus t for now. This right here is the last root that we need to find. Now, two of those multiply together, so I'm going to stop halfway here. Okay, x plus 5 times x minus 1 is going to be our r minus, plus 2. R plus 2 multiply together. Meaning what we need to have is that our, now we have an x minus 1 left, x minus 1 times x minus t must be equal to, what must it be equal to? We need to go back to our original polynomial. Our polynomial, okay, if we were to plug in r into here, we are going to get that 1 is r plus 2. R plus 2 is exactly this first part, meaning x minus x0, or I should rather say r minus x0, must be equal to x minus 1 times x minus t. And what is r minus x0? Well, let's just plug everything into here. So x squared plus 4x, and then we are going to get, on the one hand, minus 7, and then we are going to get minus x0. And now we can just multiply everything out, and let's see what t is going to be by comparing coefficients on the polynomial and what x0 must be. And then let's see if we can find another root such that 1 is a double root in this third case. Meaning if we were to multiply everything out, we are going to get, okay, x squared. Then on the other hand, we are going to get negative x, so I'm going to put a plus here, something x. We are going to get negative 1 And also we are going to get negative t times x, so negative t2. And then we are going to get, as the last part, negative 1 times negative t is going to give us plus t, must be equal to x squared plus 4x minus 7 minus x naught. Now we can start comparing coefficients, meaning we're going to get two equations. The first one being negative t minus 1 must be equal to 4 by comparing the coefficient on our x. So negative t, negative 1 must be equal to 4. And the other one is going to be that t must be equal to negative 7 minus x naught. And this is very easy to solve, obviously. We're going to add 1 on both sides, multiply by negative 1, giving us on the first equation that t must be equal to 5. Oh. And then we can already stop here, actually, because if we now were to plug this into here, 5 into here, adding x naught, we are going to get that x naught must be equal to negative 2 once again. Oh, if x naught is equal to negative 2, then t is equal to 5. This is the same as having, okay, if we were to plug, this must be negative 5, I'm sorry. If we were to plug a negative 5 into here, plus 5, this is going to give us a factorization of our polynomial P of R to be equal to a times x plus 5 squared times x minus 1 squared. We talked about this. This is exactly when x1 and x2 are double roots, meaning our third case, by doing this procedure right here, by comparing coefficients takes us back to case number 2. Meaning, under the condition that x1 equals to 1 is a double root, we also know we must have that x2 is equal to negative 5 is also a double root. I leave it as an exercise to the viewer to check the fourth case, namely that x2 is equal to negative 5 is a double root. Spoiler alert, you are going to get back to the point where we have case 2 kicking in. That x1 and x2 must both be double roots, and those are all the cases. Meaning, to give a little overview, what are the roots of our polynomial? Now the roots are on the one hand 1 and negative 5. We can have that those are both double roots, okay? Meaning our equation can either have two double roots, or if x1 and x2 have an algebraic multiplicity of just 1, then a double root lies in exactly the second case, namely x3 and 4 being equal to negative 2 if we were to plug this into here. What I find really curious is that the negative 2, the double roots here, are exactly the same as the roots of our original polynomial of degree 2. And this was a lot of casework, but I think this is the beauty of this problem. I really enjoyed this one. And if you also like what you have seen today, if you're interested in more mathematics, contest mathematics, algebra and number theory, then why not make sure to check out the contents of today's sponsor Brilliant, who are kind enough to sponsor yet another video here on this channel. Now, that was most definitely a ride this time, and I think this is by far the most favorite contest mathematics problem of mine that I have done here on this channel up to date. And if you also want to practice, for example, for Putnam, the IMO or the like, then why not check out the interactive content over on Brilliant. Interactive in the sense that you are going to use your own two hands to play around with functions and their parameters to see how they are working out under some kind of variation of parameters, you could say. How the form of a parabola polynomial of degree 2 is going to change by taking a look at this a right here and just changing it in general. I said at the start of the video that this a right here is not going to play into our roots at all, because we can factor it out at first, and under the condition that it's not equal to 0, we can just cancel it out by setting everything equal to 0. But why is it that way? Check out Brilliant and their course on parabolas, and you're going to see intuitively with a bunch of graphics how this is working out. And this is not the only instance where you can do something like this. Brilliant is just this whole platform of interactive learning content. Nearly 70 interactive courses in all topics STEM, be it the mathematics that we did today, physics, chemistry, computer sciences. No matter what it is you want to learn in the STEM field, they definitely got something up their sleeve for you. And just as a little tip, I don't know how fluent you are in the field of geometry, but this is one of my most favorite courses when it comes to their interactive content. it's just extremely cool to take a look at how you can transform the corners of a triangle and still have all those interior angles add up to 180 degrees with those nice graphics that you can witness here. And Brilliant for me is not comparable to any other website on the internet. I haven't found anything that even comes close to Brilliant and their crazy good concept. So if this feels like it's something for you, if you want to experience Brilliant firsthand with your own two hands, interactive learning content, don't forget that, then definitely make sure to check out the link at the top of the description, brilliant.org/flammablemavs. With it, you're going to get free access to a big portion of Brilliant already, but more importantly, the first 200 people to actually make use of the link get 20% of an annual premium subscription, which is a great deal, considering how much content they have available on their website already and how much content they are adding on a regular basis. It's crazy. It's a crazy good website and you should check it out to support the channel this way. And other than that, I thank you guys for watching. Don't forget to check out WAC, my mobile game, also my second channel, Flammy's Wood. And yeah, that's about it. See ya.